So we're going to start off with problems 4 now. We've already done problem 3 effectively. So we're in assignment 4, problem 4. And the key thing that I want you to pay attention to is that we are no longer determining the exact sum that something converges to. From now on, we are just going to determine whether or not the sequence converges or diverges. More often than not, you're not able to figure out exactly what it converges to. So therefore, we are just going to determine does it actually exist or does it not exist. That's going to be kind of the lion's share of the problems going forward. So when we look at 4a, we have to remember this first rule that we had about divergence, that if the sequence isn't approaching 0, there's no chance that the series can possibly converge. So when you look at a problem like 4a, I want you to see that we have something that is getting bigger in the numerator than the denominator. And we know that this is going to go to infinity. And therefore, this series must diverge. Folks, that's your first test. The first test when you're ever looking at a sequence is it approaching 0? If the sequence is not approaching 0, the series has 0 chance of converging. So that's like test number 1. And test number 2 is often, is it a geometric series too? But sometimes you don't have that as clear that it is a geometric series or not. We do know that this we know that converges. Why does it converge? Well, that is a geometric series, folks. That is a geometric series that starts at 1/2. And that just keeps on getting multiplied by 1/2 every time. So that is going to converge. And we could calculate what that converges to. But then we have to ask the next question. This converges, right? What about this? Well, sine is always less than or equal to 1. It can't be bigger than 1. So the maximum thing that the numerator on this new series can be is 1, and it's squared, so it's always going to be positive. So it's always going to be between 0 and 1. So therefore, we know that's always the case. No matter what, this new sequence is always going to be less than the geometric series of 1/2. We know this converges as a geometric series with r less than 1. We know that sine squared is always going to be less than or equal to 1. So therefore, what we know is that by the comparison test, the series will also converge. If you are always smaller than a series that converges, you also will converge. And a key thing to note, one of the conditions of the convergence test is that all terms are always positive, and this is decreasing in size too. It's very important that we recognize that it's decreasing in size and that it's approaching 0. One thing that we kind of can check pretty quickly is we see that it is approaching 0 because the denominator is getting closer and closer to 0. Okay, now we got a different one here. We know this diverges by the p-test. Right? There's a little 1 here, right? P equals 1, therefore it diverges. We know that this guy right here is always going to be at least as big as that. Why? Well, cos of x, right? This is ranging between -1 and 1, right? That's got a range of -1 to 1. So at its smallest, this numerator is 1. At its greatest, this numerator is 3. So this is always going to be at least as big as the one on the right. And therefore, by the comparison test, if you are always larger than a divergent series, or I should say larger or equal to, so greater than or equal to a series that is divergent, you also diverge. So you may say, well, what evidence do I have? Well, a key thing is you need to show the evidence here first on the left that says that, look, what I'm comparing to diverges, and it diverges by the p-test. I mean, I want to kind of show the fact that this step here of showing why the thing you're comparing to diverges is essential. It's just like this up here, showing why at 4b, that's essential. You have to show why the thing you're comparing to is converging or diverging, and then you can come around and say, hey, this guy's always greater than the one that diverges, so this guy diverges, or in 4b, this guy's always less than something that converges, so it also converges. He converges. Right? It's a geometric. R equals 1/3, which is less than 1. Okay, now what about this? So this denominator on the left side is always greater than the denominator on the right side, right? The denominator on the left side has a +1. It's bigger than the denominator on the right side. If the denominator on the left side is bigger, that means the fraction is smaller, no matter what. And this is always true, right? This is all for all n greater than 0. That's always going to be true. Actually, for all n. And therefore, we have another comparison test. Please note that when I said for all n here, we don't really need all n. We really only needed from 2 to infinity, because if you look at the initial sequence, it was from 2 to infinity. That's all we really needed. But it's for all n, obviously 2 to infinity is part of that. But when you're checking the comparison test needs to be valid for everything in the range of values that you cared about. In this case, all we cared about was 2 to infinity, because that was what was given to our initial problem. I just rewrote E to make it as clear as day. Right? By the p-test, 3/2 is greater than 1, and therefore, my 1s are looking terrible with this pen, and therefore this puppy converges. Wow, we've had a lot of converges, didn't we? Oh no, C diverged, converge, converge. All right, well, let's see what 4F is going to do. Oh, this one looks fun. See, when you look at this one immediately, you think, wow, 1 plus ln of n in the denominator, that's getting big kind of slow, right? So I want us to first focus on our instincts, right? This idea that we have the p-test, right? The p-test says that 1 over n is kind of like the threshold of speed. And we know that if we go faster in the denominator, 1 over n squared, 1 over n cubed, 1 over 3 to the n, right? These are all converging because the denominators are getting fast, right? But if we go slower than 1 over n, 1 over the square root of n, for instance, we know that we are diverging. And the things that we want to kind of get down is this instinct of what is ln of x? And 1 over ln of x is definitely in ln of n, I'm going to do. It's definitely in this camp of diverging because it's slow, right? ln of n is the slowest. It gets to infinity slower than everybody else. So we kind of have like this here is our threshold. And that threshold also diverges, right? We know 1 over n is our threshold, and that 1 over n diverges. So we kind of have like a delineation line right here. So the first thing that we want to get is this instinct of, okay, 1 over... that's terrible handwriting. Okay, so the first instinct that we want is we want to say, okay, our instinct is this guy is going to diverge. How do we prove it, right? Well, here's where it gets really hard. And one thing that we could do is we could kind of prove that 1 over ln of n diverges first and see that this guy is a little bit less than that. And that doesn't really help us, right? Because remember, when we need it to be bigger than something. And here's where it gets kind of fun. And this comparison is not trivial, and this proof is not trivial. I can talk through briefly at the end of this video. I'll talk through how you would prove it. But the one thing you can know is that this 1 over n, right? This n is getting there faster. Since n is bigger than 1 plus ln of n for all times, since n is bigger than 1 plus ln of n, we can know that since n is bigger, that this fraction is smaller. And we know about 1 over n. This diverges by the p-test. We know that diverges by the p-test, and therefore we know that the 1 over 1 plus L of n is always greater than something that diverges, so therefore this diverges by the comparison test. Now, frankly, this is the kind of stuff that in order to do this proof, it's pretty hard. To prove this statement right here, it's challenging to prove because you have to basically look at the fact that the derivative, well, long story short, hold on, let me hit pause and go to another video, another site for you. So hopefully this works. I'm in Desmos now. The blue line is y equals x, or you can treat it like y equals n, for instance. And the red line is y equals 1 plus the ln of n. And you'll see the blue line is always greater than the red line. And the reason why the blue line is always greater than the red line is because the blue is actually the tangent to the red curve. The red curve, I should call it. The blue y equals x is actually the tangent to y equals 1 plus ln of x at x equals 1. And because it's a tangent, and because the red curve is always concave down, the derivative of that is actually going to be negative. The second derivative is going to be negative 1 over x squared. And because of that, it's always negative because it's concave down and because the blue line is a tangent. That is your proof for those of you that are wondering, how do you know that? Well, y equals x is always going to be greater than y equals 1 plus ln of x, which means that the fraction, the denominator 1 over 1 plus ln of n is always going to be greater than 1 over n. So that's it for assignment 1. We'll talk to you soon.